In astronomy, the interstellar medium is the matter that exists in the space between the star systems in a galaxy. This matter includes gas in ionic, atomic, and molecular form, as well as dust and cosmic rays. It fills interstellar space and blends smoothly into the surrounding intergalactic space. The energy that occupies the same volume, in the form of electromagnetic radiation, is the interstellar radiation field. The interstellar medium is composed of multiple phases, distinguished by whether matter is ionic, atomic, or molecular, and the temperature and density of the matter. The interstellar medium is composed primarily by hydrogen followed by helium with trace amounts of carbon, oxygen, and nitrogen comparatively to hydrogen. The thermal pressures of these phases are in rough equilibrium with one another. Magnetic fields and turbulent motions also provide pressure in the ISM, and are typically more important dynamically than the thermal pressure is. In all phases, the interstellar medium is extremely tenuous by terrestrial standards. In cool, dense regions of the ISM, matter is primarily in molecular form, and reaches number densities of 106 molecules per cc. In hot, diffuse regions of the ISM, matter is primarily ionized, and the density may be as low as 10⁻⁴ ions per cc. Compare this with a number density of roughly 1019 molecules per cc for air at sea level, and 1010 molecules per cc for a laboratory high vacuum chamber. By mass, 99% of the ISM is gas in any form, and 1% is dust. Of the gas in the ISM, by number 91% of atoms are hydrogen and 9% are helium, with 0.1% being atoms of elements heavier than hydrogen or helium, known as metals, in astronomical parlance. By mass this amounts to 70% hydrogen, 28% helium, and 1.5% heavier elements. The hydrogen and helium are primarily a result of primordial nucleosynthesis, while the heavier elements in the ISM are mostly a result of enrichment in the process of stellar evolution. The ISM plays a crucial role in astrophysics precisely because of its intermediate role between stellar and galactic scales. Stars form within the densest regions of the ISM, molecular clouds, and replenish the ISM with matter and energy through planetary nebulae, stellar winds, and supernovae. This interplay between stars and the ISM helps determine the rate at which a galaxy depletes its gaseous content, and therefore its lifespan of active star formation. On September 12, 2013, NASA officially announced that Voyager 1 had reached the ISM on August 25, 2012, making it the first artificial object to do so. Interstellar plasma and dust will be studied until the mission's end in 2025. Interstellar matter. Table 1 shows a breakdown of the properties of the components of the ISM of the Milky Way. The three-phase model field. Goldsmith and Habbing put forward the static two-phase equilibrium model to explain the observed properties of the ISM. Their modeled ISM consisted of a cold dense phase, consisting of clouds of neutral and molecular hydrogen, and a warm intercloud phase, consisting of rarefied neutral and ionized gas. McKee and Oestreicher added a dynamic third phase that represented the very hot gas which had been shock heated by supernovae and constituted most of the volume of the ISM. These phases are the temperatures where heating and cooling can reach a stable equilibrium. Their paper formed the basis for further study over the past 3 decades. However, the relative proportions of the phases and their subdivisions are still not well known. Structures. The ISM is turbulent and therefore full of structure on all spatial scales. Stars are born deep inside large complexes of molecular clouds, typically a few parsecs in size. During their lives and deaths, stars interact physically with the ISM. Stellar winds from young clusters of stars and shock waves created by supernovae inject enormous amounts of energy into their surroundings, which leads to hypersonic turbulence. The resultant structures, of varying sizes, can be observed, such as stellar wind bubbles and superbubbles of hot gas. seen by X-ray satellite telescopes or turbulent flows observed in radio telescope maps. The Sun is currently traveling through the local interstellar cloud, a denser region in the low-density local bubble. Interaction with interplanetary medium. The interstellar medium begins where the interplanetary medium of the Solar System ends. The solar wind slows to subsonic velocities at the termination shock, 90 to 100 astronomical units from the Sun. In the region beyond the termination shock, called the heliosheath, interstellar matter interacts with the solar wind. Voyager 1, the farthest human-made object from the Earth, crossed the termination shock December 16, 2004 and later entered interstellar space when it crossed the heliopause on August 25, 2012, providing the first direct probe of conditions in the ISM. Interstellar extinction. The ISM is also responsible for extinction and reddening, the decreasing light intensity and shift in the dominant observable wavelengths of light from a star. These effects are caused by scattering and absorption of photons and allow the ISM to be observed with the naked eye in a dark sky. The apparent rifts that can be seen in the band of the Milky Way, a uniform disk of stars, are caused by absorption of background starlight by molecular clouds within a few thousand light-years from Earth. Far ultraviolet light is absorbed effectively by the neutral components of the ISM. For example, a typical absorption wavelength of atomic hydrogen lies at about 121.5 nanometers, the Lyman-alpha transition. Therefore, it is nearly impossible to see light emitted at that wavelength from a star farther than a few hundred light-years from Earth, because most of it is absorbed during the trip to Earth by intervening neutral hydrogen. Heating and cooling. The ISM is usually far from thermodynamic equilibrium. Collisions establish a Maxwell-Boltzmann distribution of velocities, and the temperature normally used to describe interstellar gas is the kinetic temperature, which describes the temperature at which the particles would have the observed Maxwell-Boltzmann velocity distribution in thermodynamic equilibrium. However, the interstellar radiation field is typically much weaker than a medium in thermodynamic equilibrium. It is most often roughly that of an A star, highly diluted. Therefore, bound levels within an atom or molecule in the ISM are rarely populated according to the Boltzmann formula, depending on the temperature, density, and ionization state of a portion of the ISM. Different heating and cooling mechanisms determine the temperature of the gas. Heating mechanisms. Heating by low-energy cosmic rays. The first mechanism proposed for heating the ISM was heating by low-energy cosmic rays. Cosmic rays are an efficient heating source able to penetrate in the depths of molecular clouds. Cosmic rays transfer energy to gas through both ionization and excitation and to free electrons through Coulomb interactions. Low-energy cosmic rays are more important because they are far more numerous than high-energy cosmic rays. Photoelectric heating in grains. The ultraviolet radiation emitted by hot stars can remove electrons from dust grains. The photon hits the dust grain, and some of its energy is used in overcoming the potential energy barrier to remove the electron from the grain. The remainder of the photon's energy heats the grain and gives the ejected electron kinetic energy. Since the size distribution of dust grains is where r is the size of the dust particle, the grain area distribution is. This indicates that the smallest dust grains dominate this method of heating. Photoionization. When an electron is freed from an atom, it carries kinetic energy away of the order. This heating mechanism dominates in HII regions, but is negligible in the diffuse ISM due to the relative lack of neutral carbon atoms. X-ray heating. X-rays remove electrons from atoms and ions, and those photoelectrons can provoke secondary ionizations. As the intensity is often low, this heating is only efficient in warm, less dense atomic medium. For example, in molecular clouds only hard X-rays can penetrate and X-ray heating can be ignored. This is assuming the region is not near an X-ray source such as a supernova remnant. Chemical heating. Molecular hydrogen meet This process yields 4.48 electron volts of energy distributed over the rotational and vibrational modes, kinetic energy of the molecule, as well as heating the dust grain. This kinetic energy, as well as the energy transferred from excitation of the hydrogen molecule through collisions, heats the gas grain. Gas heating collisions at high densities between gas atoms and molecules with dust grains can transfer thermal energy. This is not important in HII regions because UV radiation is more important. It is also not important in diffuse ionized medium due to the low density. In the neutral diffuse medium, grains are always colder, but do not effectively cool the gas due to the low densities. Grain heating by thermal exchange is very important in supernova remnants where densities and temperatures are very high. Gas heating via grain-gas collisions is dominant deep in giant molecular clouds. Far infrared radiation penetrates deeply due to the low optical depth. Dust grains are heated via this radiation and can transfer thermal energy during collisions with the gas. A measure of efficiency in the heating is given by the accommodation coefficient, whereas the gas temperature, the dust temperature, and the post-collision temperature of the gas atom, molecule. This coefficient was measured by as. Other heating mechanisms. A variety of macroscopic heating mechanisms are present, including gravitational collapse of a cloud, supernova explosions, stellar winds, expansion of H2 regions, magnetohydrodynamic waves created by supernova remnants, cooling mechanisms. Fine structure cooling. The process of fine structure cooling is dominant in most regions of the interstellar medium, except regions of hot gas and regions deep in molecular clouds. It occurs most efficiently with abundant atoms having fine structure levels close to the fundamental level, such as CII in the neutral medium and OII, NII, NEII and NE in HII regions. Collisions will excite these atoms to higher levels, and they will eventually de-excite through photon emission, which will carry the energy out of the region. Cooling by permitted lines at lower temperatures, more levels than fine structure levels can be populated via collisions. For example, collisional excitation of the N equals 2 level of hydrogen will release a live photon upon de-excitation. In molecular clouds, excitation of rotational lines of CO is important. Once a molecule is excited, it eventually returns to a lower energy state, emitting a photon which can leave the region, cooling the cloud. Radio wave propagation. Radio waves from 10 kHz to 300 GHz propagate differently in interstellar space than on the Earth's surface. There are many sources of interference and signal distortion that do not exist on Earth. A great deal of radio astronomy depends on compensating for the different propagation effects to uncover the desired signal. The history of knowledge of interstellar space. The nature of the interstellar medium has received the attention of astronomers and scientists over the centuries, and understanding of the ISM has developed. However, they first had to acknowledge the basic concept of interstellar space. The term appears to have been first used in print by Bacon. The interstellar sky hath so much affinity with the star, that there is a rotation of that, as well as of the star. Later, natural philosopher Robert Boyle discussed the interstellar part of heaven, which several of the modern Epicureans would have to be empty, before modern electromagnetic theory. Early physicists postulated that an invisible luminiferous ether existed as a medium to carry light waves. It was assumed that this ether extended into interstellar space. As Patterson wrote, this efflux occasions a thrill, or vibratory motion, in the ether which fills the interstellar spaces. The advent of deep photographic imaging allowed Edward Barnard to produce the first images of dark nebulae silhouetted against the background star field of the galaxy, while the first actual detection of cold diffuse matter in interstellar space was made by Johannes Hartmann in 1904 through the use of absorption line spectroscopy. In his historic study of the spectrum and orbit of Delta Orionis, Hartmann observed the light coming from this star and realized that some of this light was being absorbed before it reached the Earth. Hartmann reported that absorption from the K line of calcium appeared extraordinarily weak, but almost perfectly sharp, and also reported the quite surprising result that the calcium line at 393.4 nanometers does not share in the periodic displacements of the lines caused by the orbital motion of the spectroscopic binary star. The stationary nature of the line led Hartmann to conclude that the gas responsible for the absorption was not present in the atmosphere of Delta Orionis, but was instead located within an isolated cloud of matter residing somewhere along the line of sight to this star. This discovery launched the study of the interstellar medium. In the series of investigations, Victor Ambartsumian introduced the now commonly accepted notion that interstellar matter occurs in the form of clouds. Following Hartmann's identification of interstellar calcium absorption, interstellar sodium was detected by Hager through the observation of stationary absorption from the atoms D lines at 589.0 and 589.6 nanometers. Towards Delta Orionis and Beta Scorpii. Subsequent observations of the H and K lines of calcium by Beals revealed double and asymmetric profiles in the spectra of Epsilon and Zeta Orionis. These were the first steps in the study of the very complex interstellar sight line towards Orion. Asymmetric absorption line profiles are the result of the superposition of multiple absorption lines, each corresponding to the same atomic transition, but occurring in interstellar clouds with different radial velocities. Because each cloud has a different velocity, the absorption lines occurring within each cloud are either blue-shifted or red-shifted from the line's rest wavelength. Through the Doppler effect, these observations confirming that matter is not distributed homogeneously were the first evidence of multiple discrete clouds within the ISM. The growing evidence for interstellar material led Pickering to comment that, while the interstellar absorbing medium may be simply the ether, yet the character of its selective absorption, as indicated by Cap 10, is characteristic of a gas, and free gaseous molecules are certainly there, since they are probably constantly being expelled by the Sun and stars. The same year Victor Hess's discovery of cosmic rays, highly energetic charged particles that rain onto the Earth from space, led others to speculate whether they also pervaded interstellar space. The following year the Norwegian explorer and physicist Christian Birkeland wrote, "It seems to be a natural consequence of our points of view to assume that the whole of space is filled with electrons and flying electric ions of all kinds. We have assumed that each stellar system in evolutions throws off electric corpuscles into space. It does not seem unreasonable therefore to think that the greater part of the material masses in the universe is found, not in the solar systems or nebulae, but in empty space." Thorndike noted that, "It could scarcely have been believed that the enormous gaps between the stars are completely void. Terrestrial aurora are not improbably excited by charged particles emitted by the Sun. If the millions of other stars are also ejecting ions, as is undoubtedly true, no absolute vacuum can exist within the galaxy." In September 2012, NASA scientists reported that polycyclic aromatic hydrocarbons, subjected to interstellar medium conditions, are transformed, through hydrogenation, oxygenation and hydroxylation, to more complex organics, a step along the path toward amino acids and nucleotides, the raw materials of proteins and DNA, respectively. Further, as a result of these transformations, the PAHs lose their spectroscopic signature, which could be one of the reasons for the lack of PAH detection in interstellar ice grains, particularly the outer regions of cold, dense clouds or the upper molecular layers of protoplanetary disks. In February 2014, NASA announced a greatly upgraded database for tracking polycyclic aromatic hydrocarbons in the universe. According to scientists, more than 20% of the carbon in the universe may be associated with PAHs, possible starting materials for the formation of life. PAHs seem to have been formed shortly after the Big Bang, are widespread throughout the universe, and are associated with new stars and exoplanets.